Hello, Year 11, and welcome to our next video here on functions and their graphs. We're looking at powers, polynomials, and circles today. A mix of different functions, I suppose. And we're going to push on with, beginning with the square root of x. So if y equals the square root of x. Now, x equals y squared looks pretty similar, right? X equals y squared, but it's not exactly the same. So let's consider, what if x equals 4? Well, that could equal 2 squared, or it could equal negative 2 squared. So one value of x could map to two different values of y. That would mean it's failing the vertical line test. So x equals y squared isn't a function, but y equals the square root of x is slightly different because we're only considering here the positive square root. Okay, and here's a graph of it. This is y equals the square root of x. You'll see it looks a lot like a parabola on its side because it is. Well, at least half of one. Okay, so we've just got half a parabola there. We've taken the top half. I could have y equals negative root x, and that'd be fine as well. It would be the bottom half. That would also be a function. If we look at the domain, we can see, in this case, if y equals square root of x, the domain is x is greater than or equal to 0. Okay, no negatives going in there. And my range, in this case, is going to be y is greater than or equal to 0. There we go. So y equals the square root of x is a function, but x equals y squared is not. Now, y equals x cubed. This is a polynomial. We've dealt with some of these before. This is nice and simple. We've got a graph here. We should be familiar. Okay, y equals x cubed. Right, third degree polynomial. A 0 of multiplicity 3 at the origin. Sounds very flash, doesn't it? Anyhow, this is y equals x cubed. We can see vertical line test passes fine. Okay, it is a function. The domain, all values of x, and the range, all values of y. This funny shaped curve in the middle here, right? We call that a horizontal inflection, and it's important that you remember that term for later on, perhaps. Okay, but y equals x cubed. Okay, that is a function, certainly. Moving along now to y equals x to the power of 4. Okay, y equals x to the power of 4. Like this, we can see it looks a bit like a parabola, a bit like a quadratic in that sense. But the sides are a bit steeper and the bottom's a bit flatter. Right? That's the main thing to take on there. It has domain of all values of x. Its range, however, is greater than or equal to 0. Okay, y equals x to the power of 4. Circles and semicircles, so there's a lot more analysis to be done here. So let me just get my head out of the road there. Circles and semicircles, what's all this about? Well, if I have a circle with a centre at AB and a radius of r, then the equation for that circle is x minus a squared plus y minus b squared equals r squared. So a and b are the centre, or if you like, they both describe a translation in the x-axis and the y-axis. Right? A moves it to the right and b moves it up the centre of that circle, and r squared is the radius. There is a relationship here to Pythagoras' theorem as well, and I suppose we'll probably get to that later in this exercise. A circle, of course, will fail the vertical line test. Okay, we know that we could cut that circle twice with vertical line, but if I just take the upper half of the circle, right, the top semicircle, then I will have a function, much like we did with y equals the square root of x. Okay, now rearranging this formula here, we would get something like y equals the square root of r squared minus x. I haven't got any translation involved in that. That's centre. That is the centre at the origin. Now I think we have an example here that we're going to have a look at, and it's reasonably complicated. Let's see. Move this over here. Now, the centre and radius of this circle, we need to find that. What's going on here? That isn't in the right format at all. Okay, it's not just x squared plus y squared equals r squared. So the centre isn't the origin. I've got this minus 8x and this plus 6y. That's not very helpful to me at all at this stage. What I'm going to need to do is to complete the square for x and for y, and that should produce a radius for me. Okay, let's get this out of the road again. So first of all, let's have a look at that. We're going to complete the square, and you can see here, I halve the negative x, gives me negative 4, square it, 16 minus 16. Now, I've got the 6y, half of that is 3, square it is 9 minus 9, and equals 0. So I have a nice perfect square here, which should be x minus 4 all squared. A nice squared here, perfect square here, y plus 3 all squared. Okay. And then the negative 16 minus 9 is negative 25. And if I add that to both sides, right, now we're set up here. So I can see the centre is at 4, negative 3, and the radius is 5. I need to sketch this now. Let's begin perhaps by letting y equals 0 to find the x-intercepts. So if I substitute y equals 0 in there, I end up with this expression. And, right, when I solve that, whoops, I've skipped a step, let's just go back a moment. When I solve that, I get x minus 4 equals 4, or x minus 4 equals negative 4. Right, that's 9. I took 9 away from both sides, and I got 16. That means that x is either 8 or 0. Now, we could do the same, let x equals 0 to find the y-intercepts. We've already got one because I let y equals, we see here, when y equals 0, x equals 0, that means that this passes through the origin. And in fact, we might have worked that out anyway. Consider the distance from the origin to this point. Okay. We can use Pythagoras' theorem, right? The distance between 2 points, or the distance formula, the distance is the change in x squared plus the change in y squared, and then square rooted. So 4 squared plus negative 3 squared equals 25. The square root of that is 5. So we can see here, with that centre, we should pass through the origin anyway. So let's have a look at a little picture here and move my head out of the road. So here's my centre at 4, negative 3. 4, negative 3, there's the centre of my circle, passes through the origin. Now we calculated here that I have another intercept at 8, and I probably could have got by without that, but anyway, we've got this point, and now, because my circle is very symmetrical, then if I go from 0 to 4, I'll also go from 4 to 8 to the next intercept. From 0 to negative 3 to negative 6. I haven't calculated that there, at least not directly, but those are going to be my intercepts. So there's a little bit of work there, and I suppose you could argue that's not a function. Why are we dealing with that? Well, it's a relation, it's important, and it's a nice application of completing the square. I hope that's helpful. If it's not, try watching it again, I don't know. No, that should be helpful. If you do have some questions about it though, please jot them down and either ask me in class or send them to me. Okay, thanks very much. See you next time.